Hello, in this video we will make observations and notice patterns in the graphs of polynomial functions. We will use our observations to make generalizations about the connections between a polynomial's degree, number of possible real zeros, turning points, and the multiplicity of zeros. To begin, recall that any value of x for which p of x equals 0 is called a zero of the polynomial p of x. Graphically, a real zero of a polynomial is any x value that makes the output equal to 0. An x-intercept. Pause the video and determine the number of unique zeros for the fifth degree polynomials below. Okay, you notice that from left to right, these fifth degree polynomials have 1 0, 2 zeros, 3 real zeros, 4 real zeros, and 5 real zeros. You may be wondering if a fifth degree polynomial could have 6 real zeros. Recall from our previous work that the zeros of a polynomial are related to the factors of the polynomial. If a polynomial has 6 unique real zeros, then there would be 6 factors, making it a sixth degree polynomial. Thus, we can make the generalization that a fifth degree polynomial could have 1, 2, 3, 4, or 5 real zeros. We could also think about a degree 2 polynomial, a quadratic. We know that quadratics can have either 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. Right? So a degree 2 polynomial could have 0, 1, or 2 real zeros. These generalizations can be applied to all polynomials, and it is called the fundamental theorem of algebra. Namely, any nth degree polynomial p of x has at most n real zeros. Next, we're going to look for a relationship between the number of turning points and the degree of a polynomial. Pause the video and determine the number of turning points for the fifth degree polynomials and then the fourth degree polynomials below. We notice from left to right that the fifth degree polynomials have 0 turning points. So this little change in shape is not actually a turning point. 2 turning points. The third graph also has 2 turning points. And then 4 turning points and 4 turning points again. The fourth degree polynomials have 1 turning point or 3 turning points. If we added one more turning point to these last graphs, we would create an additional x-intercept, which in turn would increase the degree of the polynomial. Thus, we can conclude that the fifth degree polynomials have at most 4 turning points, and the fourth degree polynomials have at most 3 turning points. It's also worth noting that the number of turning points seems to change by 2. The fifth degree polynomial had either 0, 2, or 4 turning points, while the fourth degree polynomials had either 1 or 3 turning points. These observations can also be generalized and proven for all polynomials. In general, for all polynomials, we can conclude that the maximum number of turning points of a degree n polynomial is n minus 1. In other words, the maximum number of turning points is 1 less than the degree of the polynomial. Moreover, if the degree n is even, then the number of turning points is either n minus 1, n minus 3, etc., till we get down to 1 turning point. We saw this with the degree 4 polynomial. It had either 4 minus 1, which equaled 3 turning points, or 4 minus 3, which equaled 1 turning point. And if the degree n is odd, its number of turning points is either n minus 1, n minus 3, etc., down to 0 turning points. And we saw this with the degree 5 polynomial. It had either 5 minus 1, which equals 4 turning points, 5 minus 3, which equals 2 turning points, or 5 minus 5, which equals 0 turning points. The final observation we want to make is between the multiplicity of the real zeros and the shape of the graph at the corresponding zeros. We will let p of x equal x plus 1 raised to the m times x minus 2 raised to the n. So m is the multiplicity for x plus 1, and n is the multiplicity for x minus 2. There's a real zero at x equals negative 1 and at x equals 2, and currently the multiplicity of both of those zeros is 1, because you'll notice m is equal to 1, and then n is also currently set equal to 1. And you'll notice that if we zoom in at both of the real zeros, the graph appears to be linear, which is a first degree polynomial. If we increase the multiplicity of x plus 1 to 2, we now see that the graph behaves like a quadratic, which is a second degree polynomial near x equals -1. The same thing happens if we change the multiplicity corresponding to x equals 2. Now the graph looks like a parabola near the x-intercept at x equals 2. I'm going to slowly increase the multiplicity of x plus 1 to the m and observe how the graph behaves at the related 0 of x equals -1 as the multiplicity increases. 4, multiplicity 5, 6, 7, and 8. Now I'll slowly increase the multiplicity for x minus 2, and again observe how the graph changes at the x-intercept to 0. So multiplicity 2, 3, multiplicity 4, 5, multiplicity 6, 7, and 8. Hopefully you noticed that when the multiplicity is even, the graph bounces off the x-axis, and when the multiplicity is odd, the graph passes through the x-axis. Furthermore, you may have noticed that as the multiplicity increased, the graph appeared flatter near the x-intercept. You may find it useful to rewatch this animation and look for these behaviors again if you did not notice them the first time. In summary, if x minus r raised to the nth power is a factor of a polynomial p so that x equals r is a 0 of multiplicity n, then when n is even, the graph will bounce off the x-axis. When n is odd, the graph will pass through the x-axis, and as n increases, the graph appears flatter near the x-intercept, x equals r.